Okay, so this topic is very similar to equilibrium in some ways, which is why I always do them back to back, because I feel like it's easier to keep them apart in your brain if you do them back to back than if you do them like a month or two apart. So if you remember, that's not what I wanted to do. All right, so let's just do a generic equation. That's a G. Gas yields 3C gas, right? Just a generic equation. So if you remember, for equilibrium, that would be K equals C to the third over A squared times B, right? So stuff on the right goes on top, stuff on the left goes on the bottom. The C is to the third power, the B is to the first power, and the A is to the second power. Okay, that's equilibrium. Well, what we're going to do now is called rate law. Rate law. And so here's what the rate law for this would be. The rate law for this would be rate equals K times A times B, and that's an M and an N above it. Which I'm going to explain all this, so don't freak out. All right. So there's a couple differences, right? So equilibrium, right? It's K equals top over bottom, and the coefficients are exponents, right? That's how equilibrium worked. Well, rate law, it's top over bottom. That's hilarious. Of course it's top over bottom. That's the definition of top and the definition of bottom. How about it's right over left? There we go. Okay. Whereas the rate law, it's only the left side. Okay. We don't care about the right side at all. And the exponents are called, I'm going to put it in quotes here, are called orders. All right. They're called orders. And orders have to be found experimentally. Okay. You cannot look at this and know what these exponents are going to be just by looking at it. You have to have data. You have to have experimental data to determine these M and N. And again, right, if there's only one, right, if there's only one thing on the left, there's only one thing in the equation. If there's 7 things on the left, there's 7 things in the equation. Right, just everything on the left multiplied together to the power of their order. You still have no idea what order is. I haven't told you about order yet. You're about to figure it out, but as of right now, you don't know anything about order, and that's totally fine. Okay. You got 5 seconds to speak up before I erase this. Does anybody have any questions? Comments? Okay. And it's all erased. Oh my gosh. It's my new favorite magic trick. Do this. Because you can't see that I'm not actually erasing. Anyways. Okay. So we have to we got to keep entertained during the quarantine, okay? Gotta find something to entertain us. Oh no, I erased half my equation. I got a little carried away with my erasing. Okay. So here's what you have to be given. You're going to be given a table. Every time it's going to look exactly like this. It's going to look literally exactly like this. So first I'm going to rewrite the rate law equation for this, right? It's rate equals K times A to something we don't know yet, and times B to something we don't know yet. So I'm just not going to put anything there, and we're going to fill it in a second. Now, you're going to be given a table that looks like this. Experiment, concentration of A, concentration of B, and rate. So basically, what you have to do in the real world, if you want to figure out the orders, and again, if we were in class, we would do this. What you have to do, first off, what does rate mean? What is the rate of a reaction? What do you think that means? What do you think that another word for that? Any guesses?
How quickly it happens?
Yeah, how quickly it happens. Speed, right? Rate and speed. Rate and speed are synonymous. You can't stand these markers up. I guess they're too rounded. Disappointment. We're all disappointed. So it's how fast it goes. All right. So basically, what you do is in the real world, you would do this reaction. Let's just say we put two A's and two B's together, and we measure how fast that reaction happens. So now what you do is you do it a second time, but you keep one of them the same, but you change one of them. And then you do that reaction again and see how the rate changes. So there are three orders that we're going to worry about in this class. There is zeroth order. Yep, I said zeroth. There is first order, and there is second order. Okay, these are the three orders that we are going to deal with in this class. You take chemistry in college, you're going to deal with more orders, and it's going to be a little more complicated, but not for us. So here's the thing. What happens, and so these are great, 0, 1, or 2 are going to be your exponents. It's either going to be a 0, a 1, or a 2. So what happens if you put something to the 0th power? Does anybody remember from math class? If something's to the 0th power, what it becomes?
It just becomes 1.
It just becomes 1. So what that means is, do you see if we're multiplying, what happens to rate if I multiply by 1? What happens to any number if you multiply by 1?
It stays the same.
It stays the same. So if B is 0th order, that means you're multiplying your rate by 1. So in this case, this would be an example of a 0th order reactant. So 0th order is when there's no change in rate. All right. So here we doubled B, but rate didn't change. So B must be 0th order. So we can put a 0 up above there. Okay. Now, the other one is first order, meaning let's say we keep our B the same, but now we double A. When we double A, again, I'm comparing from 1 to 3, right? When we double A, if our rate doubles, then that means it's first order. So when your rate change equals your, I don't know what I want to call this, reactant change. Now, the mistake people make is they want to think about adding and subtracting. It's always multiplying and dividing. This is not adding 2. See, what people are going to do is they're going to say, oh, you added 2 and you added 4. They're not the same. Don't think it's multiplying. You multiplied by 2, you multiplied by 2. So that means A is first order. It's kind of hard to read. I'm going to erase now just so we can do more practice. And actually, I think I'll just keep the first row just to keep it easy for me. Okay. So now, obviously, I haven't talked about second order now. So now I'm going to talk about second order. So this is when there's no change in rate. This is when rate changes, but it changes the same amount. This is when, for our purposes for this class, if it's not zeroth or first. Right, I'm making it real easy. So check this out. Let's say I keep B the same, but I double A. And rate goes to 16. So here's what you would do. You would say, okay, A was multiplied by 2, and rate was multiplied by 4. So it's not zeroth because there is a change. It's not first because the change isn't the same. So it must be second. So in this case, A is second. And so now to find B, again, so to find B, you need to find 2 experiments where A stays the same and B changes. So again, we want to compare 1 and 3, right? We can't compare 2 and 3, but we can compare 1 and 3. So between 1 and 3, B doubles and rate doubles. So the rate change is equal to the reactant change. So B is first order. All right. So now, really the only thing you have to do, the only other thing that's a part of this is calculating K. So to calculate K, you can calculate K plugging in any of these, as long as you stick in the same row, right? If you think about this, you have rate, you have A, you have B. So you can plug in the data from experiment 1, from experiment 2, or experiment 3. If you do any of these in there, you will get the same exact answer for K, I promise. My opinion is just to always use the smallest number. That's just easier. So like I'm going to use experiment 1. So to calculate K, I'm just going to plug in everything from experiment 1. So rate is 4. So 4 equals K times A is 2, and it needs to be squared, times B, which is 2. So 4 equals, what is that, 16K? No, 8. 8K. So K equals 1/2. Like I said, you could have totally done this one too. This would have worked as well. I'll show you. 8 equals K times 2 squared times 4. 8 equals 16K. K equals 0.5. And trust me, we could have done it with 2 as well, but I'm not going to keep doing this because it's a waste of everybody's time. But so it doesn't matter which one of these you pick, as long as you keep it all right. Only use these values with these or these or these. You can't be like picking like this A and this B and this, like that doesn't work. All right. Any questions before I kick it up a notch? by the way, guys, it doesn't get much harder. Like this is like, don't be afraid that I'm kicking it up notches because it's really not much more. You can't really be much more difficult for this. I'm just going to make it a 3 variable equation instead. So I'm just going to add a C. And then a rate. Okay, same thing, just change the numbers a little bit here. And we'll need probably 2 more rows along the bottom. Okay. So same thing. First you need to do is find the orders. In order to find the order, you need to find 2 experiments where only one of them changes. So let's 3, 1, 2. All right, so just bear with me for a second. I'm going to fill this table out just to show you what you're going to see on a test or a quiz or your homework or whatever. This one's kind of tricky. Let's do. Okay, done. So this could be a test question. This could totally be a test question. So what we want to do, and actually I have a little trick to make this. I'm writing the same exact thing there, so don't worry about erasing this. I'm just doing it in a different color, and you'll see why in a second. I'm going to use this beautiful aquamarine kind of teal color for A. And then I will use this kind of pinky, magenta-y, whatever color for B. I'm also kind of stalling to give you a second if you're writing anything down. And I will use this violet. You're turning violet for C. Okay. So what we need to do any of you get that reference, violet, you're turning violet? Anybody at all? Probably not. That's okay. I'm old. I can live with it. So what we're going to do is we want to figure out, right, our rate law equation. Rate equals K times A times B times C, and we want to find the exponents. So what we're going to do is we need to find 2 experiments. Let's do A first because that's the pen I grabbed. 2 experiments where only A changes, right? Where B stays the same and C stays the same. So thankfully, 1 and 2 work. It's not always going to be that case where they're right next to each other. It's actually very often not going to be that case, but I made it that way for you. So this is why I have the colors, and it'll make sense in a second. So we multiplied by 2, right? 3 to 6, we multiplied by 2. What happened to our rate when we multiplied by 2, right? We check out the rate. I'm actually going to get rid of this line because it's going to cause problems. You see, when we multiplied by 2, there's no change. Right? No change. We multiplied by 1. Right? So no change. So since there was a change in A, but no change in rate, A is 0th order. Now let's do B. We need to find 2 experiments where only B changed. Right? So we can't do 2 and 3 because A changed and B changed. We can't do 3 and 4 because, well, they all changed. Right? So what we have to do is 1 and 3. So compare 1 and 3. A stayed the same, C stayed the same, B doubled. When B doubled, rate also doubled times 2. So since they both did the same thing, B is first order. Now, if you have some test taking strategies, you can probably guess what C is going to be because I wanted to give you an example of each order, but we'll do it anyways. So again, you want to find 2 experiments where only C changed. So 2 and 4, right? A stayed the same, B stayed the same, C changed. So I'll make a little pathway boop, right? Going between, right, 2 and 4, B doubled. Going between 2 and 4, sorry, you're just gonna have to do this. Going between 2 and 4, this went, I wrote times 4, but it should say times 2. I don't know, because I was thinking about this one. Right? So since when you doubled C, you quadrupled your rate, C is second order. All right. Before I move on, I would love to take any questions you might have about that. Okay. So now what we're going to do is we need to calculate K and we need to find this missing value. All right. So first let's calculate K. So all we're going to do is we're going to take any one of these and just plug them in. Again, I like to go with the smallest, easiest numbers. So experiment 1 happens to be the case this time. It won't always be the case, but it is this time. So I'm just going to plug this in. Rate is 8. So 8 equals K times 3 to the 0th. So if something is to the 0th power, you don't even need to put it in there because it's automatically 1. Like it doesn't even matter. So I'm not even going to put it in there. So there would be an A there, but we know it's a 1, so it doesn't matter. B, right? B is 1 times C, which is 2 squared because it's second order. So this becomes 8 equals K times 4. So K equals 2. Perfect. So now all we do to find a missing one is we just plug it all back in, just like we just did, except now we know K, so we can find that. So if we plug this all in, rate is 40, right? So 40 equals K, which is 2, times A, which is 3 to the 0th power, so we don't have to put it, times B, which is 2 to the first power, times C, which is what we're trying to find. So 40 equals 4C squared. So 10 equals C squared. So we would just take the square root of 10 to get C. All right, how are we feeling about that?